Hello everyone, and welcome to a discussion of circular orbits. So consider, as in the picture here, that the apple is moving in a circular orbit around the Earth, and that the orbital radius of that apple is r, which means that r is both the radius of the apple's orbit and the distance from the center of the Earth to the center of the apple. Those are the same two values. Now this apple will of course have a force of gravity acting on it from the Earth, which will act straight down towards the center of the Earth. And no matter where that apple is in its orbit, that force of gravity will always point inward. So we have the inward directed net force provided by the force of gravity. Now, since it is accelerating, after all it's changing direction, Newton's second law tells us that the net force is equal to the mass times the acceleration of the apple. There is only one force, which is the force of gravity. And the mass here is the mass of the apple. And the acceleration is not just any acceleration. This is the inward directed acceleration of an object moving in a circle at a constant speed. In other words, this is the centripetal acceleration. Now, of course, we know two things. We know an equation now for the force of gravity using the law of universal gravitation. And we know that the centripetal acceleration can be written as speed squared over the radius. So here's the force of gravity using the law of universal gravitation. The gravitational constant times the mass of the apple times the mass of, in this case, the Earth or whatever planet's being orbited, divided by r squared, equals the mass of the apple times its speed squared, and I'm using a little o here for orbital speed, divided by the radius of the orbit. And notice here that these r's in this case, even though they are two different things, this r is the distance from the center of the Earth to the center of the apple, is the same as this r, which is the radius of the orbit. They're the same number in this case. Notice that the mass of the apple cancels out, which means that it doesn't matter how much mass the orbiting object has. Its speed will need to be the same. Also, one of the r's cancel. And so we are left with the orbital speed squared is equal to the gravitational constant times the mass of the planet divided by the radius. Take a square root, and we get our final equation. That the orbital speed, the speed required, right, sideways tangential speed, needed to make an orbit around a planet of mass m at radius r is equal to the square root of big G m over r. So this is the orbital speed of a circular orbit. Right, the constant speed it needs. This is, in other words, the sideways speed it needs so that it will miss the Earth as it moves fast enough sideways, but constantly being pulled inward. So again, this is a nice equation you can plug numbers into. This is the mass of whatever planet's being orbited. This is the radius of that orbit, how far apart the object is from the planet or sun or whatever it is. Right? And we can do this also proportionally thinking. You know, if one's doubled, what happens, that kind of thing, which you'll see in the MOPs. Now, one additional thing. Remember here that since this is moving in a circle, it's moving at constant speed. And generically, as we learned back in the toy car lab, constant speed is just distance over time. Well, if something's moving in a circle, the distance it moves one time around is the circumference of the circle, and the time to go around once is called the period. So you can calculate this constant speed by using the equation we just had, or by taking 2 pi times the radius over the period. Putting those two things together, substituting this in, we get the quantity 2 pi r over the period, quantity squared, equals big G, mass of the planet, over r. Square it, we get this. Same thing right here. And now I'm going to do some algebra. I'm going to move the period squared over here, and I'm going to move r up there, g down there, and m down there, and flip the sides. Now, take a look at what we have. On this side, we've just got period squared, and over here, we've got radius cubed. And then we have this quantity, 4 pi squared, gravitational constant, mass of the planet or sun that's being orbited. This is a constant. So therefore, this equation is saying that the period squared of an orbiting thing is proportional to its radius cubed. I hope that sounds familiar. That's Kepler's third law. So what we've just done is proven that the law of universal gravitation, as derived by Isaac Newton, leads us to Kepler's third law. And this is a more powerful version of Kepler's third law, because not only does it tell you that the period squared and the radius cubed, or semi-major axis if it's an ellipse, are proportional to one another, but it tells you what that constant of proportionality is, what the slope of the period squared versus radius cubed graph would be, if you will. So let's use this to solve a problem. Let's figure out what the mass of the sun is, given that the Earth's distance from the sun is about 1.50 times 10 to the 11th meters. Again, that's a number that the ancient Greeks knew. Now, they didn't know it that perfectly, but they had a pretty decent approximation for how far the sun was away from the Earth by doing geometry on shadows on the Earth. You can look that up on Google if you want. So, first of all, the Earth is orbiting the sun, so the period squared of the Earth's orbit around the sun must be equal to 4 pi squared over big G times the mass of the sun, that's the mass being orbited, times the radius of the Earth's orbit cubed. Now in this case, since the Earth goes in a basically slightly elliptical orbit, not very, remember, it's like 0.0167, it's only 1.7% eccentric, we're going to approximate it as circular and just make life easy. So this would be the average radius, if you will. Solve for the mass of the sun, move the period squared underneath, move the mass over here, and then we can plug our numbers in. But we have to realize that, of course, it takes the Earth 1 Earth year to go around the sun. That's 365.24 days, 24 hours in each day, 60 minutes in each hour, 60 seconds in each minute. If you do all that conversion, you get about 3.16 times 10 to the 7th seconds in 1 year. Plug all that in. We need to be in seconds because we have newtons in here, which are kilogram meters squared per second squared, kilogram meters per second squared. So we need seconds. So here's the radius of the Earth's orbit around the sun. Here's the gravitational constant. Here's the period of the Earth around the sun squared. And we get a mass of the sun of about 2.0 times 10 to the 30th kilograms. Now before you think, hey, that's less than the Earth, because the Earth was roughly 5.98. Remember that the Earth was only times 10 to the 24th kilograms. This is times 10 to the 30th kilograms. Right? That's an extra 10 to the 6th. That's an extra million times bigger. Right? So the sun is much more massive than the Earth. So notice here how we can use Kepler's third law. And the cool thing about this version of it is that you don't need to compare it to any other object orbiting the sun. You can just look at one object at a time. But you got to be careful. This is the period of the object orbiting whatever's being orbited, the sun or the planet. This is the mass of the thing being orbited. So notice we didn't have to use the mass of the Earth in here anywhere. And this is the radius of the orbit. It'll also work for the semi-major axis. So here again, trying to show you that the law of universal gravitation leads to consequences that we've already seen, like Kepler's third law. Enjoy your next worksheet and the last couple of MOPs.